So now let's take a look at dynamic games. And so dynamic games are going to be a little weird when we start to think about how exactly to do everything. And so dynamic games are happen when players move sequentially or repeated. So imagine me and Sam are playing a game. We're going to move. I'm going to go first. Sam's going to go second. That would be sequentially. Or imagine that I go first, Sam goes second, I go again, Sam goes again, I go again, Sam goes again. That would be repeatedly. Another way that we could have repeatedly is we're going to play the static game one time, and then we're going to replay the static game another time, and then we're going to replay the static game the third time. So we could still be acting simultaneously, just over and over and over again. And that's more typically for what you see in a repeated game. But players are still going to have complete information about payoff functions. And at each move, players are going to have perfect information about what happened previously. And so dynamic games are analyzed in an extensive form, from which we call a game tree, and static games are analyzed in a normal form, for which we call the payoff matrix or the game box. So let's think about this. We had this game box, right? This would be in the static game. If we wanted to solve this statically, right, let's assume that LG is not going to enter. Let's assume that LG is not going to enter. So Panasonic should enter. If LG is going to enter, then Panasonic should not enter. Similarly, if Panasonic is going to enter, LG would be better off not entering. And if Panasonic is not going to enter, though, LG would be better off entering. Right? And so now, if we were working together, like and both people were making a decision, they would have that like weird, well, I would enter if nobody else is going to enter, but now I'm not going to enter if I'm not going to enter. Right? And so this is where we are going to get into something called the sequential component. Let's assume that LG is what we call our first mover. So LG moves first. They get a choice to enter or not enter. And then Panasonic gets to choose. And again, they get very similar things where they can choose to enter or not enter. Enter or not enter. And so I guess we could make these different colors if we wanted to. That way we can see the payoffs a little bit better. So for each of these potential branches, we have potential outcomes. If LG moves, if LG decides to enter and Panasonic enters, they both get minus 120. Right? That would be this box here. If LG enters, but Panasonic doesn't enter, LG gets everything, Panasonic gets nothing. If LG doesn't enter, but Panasonic enters, then we get something like this. And if LG doesn't enter and Panasonic doesn't enter, then both guys are going to get 0 and just walk home. And so the way that we solve this is by what we call backwards induction. And so let's first point out a couple things here first. These components here are called decision nodes. I guess let me use like maybe green would be better. Yeah, these green spots are called decision nodes. Decision nodes identify the player, so LG or Panasonic, that is making the decision at that moment in time. And then at each decision node, there is a potential action that each person could take. Right? And so similarly, at each decision node, there's 2 actions that everybody can take. And then at the end, these are going to be the payoffs. And they match the static game box, but the difference is that now we are able to move sequentially. So if LG moved first, And the way that we solve these is we're going to do a thing called backwards induction. So let's look here. Assuming LG entered first, Panasonic would be better to just stay home. Man, that is a bad color. If LG didn't enter, Panasonic would be advantageous to enter. And then, so now we know that we are here or we are here. And so now LG makes its decision. Do they want 1200 or zero, right? Should they enter or should they not enter? Well, obviously, LG is then going to enter. And so this would be our final outcome. That would be our final choice for this game tree. And so in this, so that would be like a sequential game. So that would be the first mover advantage in practice. In a repeated game, a firm can influence its rival behavior by signaling and threatening to punish. And through signaling, our goal is to get to players to cooperate and to achieve the highest joint payoff. And so signaling then would be a good example of how do we get the prisoner's dilemma, the strategy to collude. So suppose that these two prisoners have a large history of doing bank robberies together, right? So they can play the game previously and send a positive signal. So suppose like they play this game over and over and over again, right? If they don't confess, don't confess, don't confess, don't confess, don't confess, don't confess. By signaling to each other prior that they're going to work together, they will not confess. However, let's suppose that here, this person, this second player, or this first player is going to confess. So if we remember, oops, the payoffs in these were 1 year in jail, 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 1 year in jail. This is now 0 years in jail, 20 years in jail. Once that dude gets out, there is no way that he is going to go back to not confess, not confess, because he's not going to risk his chance on that one more time, right? That dude broke his trust. And so forever, now it's going to be 5 years in jail, 5 years in jail, 5 years in jail, 5 years in jail, right? So by sending a positive signal over and over and over again, you get to be a more socially optimal decision. However, when you first deviate from that optimum, there is no way for you to go back. This is what we call a grim trigger strategy. And in the real world, this is often seen in price matching. So if you ever go to a grocery store or like a Walmart and you're like, hey, I found this for a lower price elsewhere, then Kmart, before it went out of business, screwed Walmart, and now Walmart is always going to offer at that low price, and so they're going to pull more business away from Kmart, right? And so that would also be a grim trigger. And so these threats have to be credible, right? The credibility of a threat is the perceived likelihood that the threat will be carried out if the conditions that are supposed to trigger it are met. And so when people believe that a threat will be carried out and it is credible, when they believe that it's a bluff, the threat is not credible. And so the credibility all depends on the audience's perception. And so let's think about repeated games for finite and infinite games, right? And so when we're thinking about this, let's go back to our advertising effect. Like, let's go back to the advertising game. So let's say that there are two players, G and R. Um, so they can advertise or not. If they both advertise, then they're going to go 4-4. Or, sorry, if they both don't advertise, they'll go 4-4. We're going to use the shrinking one. If one of them advertises, but the other one, if they both advertise, it's going to be 1-1. If one of them doesn't advertise, but the other one does, they are going to take everything. And so in the static game, remember, we said that the 1, 1 was the Nash equilibrium, right? If you want to like go back to video one to see why that is, here. In an infinite game, what is going to be the Nash equilibrium? Well, in an infinite game, so a game that has no end, it is going to be not advertise, not advertise. So this would be the static Nash equilibrium. And again, that would be our, by going not advertise, not advertise, not advertise, not advertise forever, we're playing the game exactly how people would expect us to play the game, and we're playing the game cooperatively. However, what if, how many periods of advertise does it need to be to ensure that there is a credible threat to ensure this dynamic equilibrium? And this only says one. We only need one period of advertise to do this, right? So if, again, coming back to this prisoner's dilemma, suppose that one person deviates, well, then in the immediate next round, it's going to be advertised forever. Because why would we assume that this person is going to jump the other way when he screwed us, right? And so, what is the Nash equilibrium game if this game is only repeated a finite number of times? This is going to be advertise, advertise. And here's why. If we know that this game is only going to be repeated for 3 rounds, okay? So let's say that this game is only going to be repeated for 3 rounds. In the last round, why does it matter what the other person's going to do? We're going to try to advertise. And both players are going to assume that the other person is going to try to, I mean, that they should advertise because they are going to want to try to get to this box here, right? They are going to want to super, super hard try to get to this box here. And so one step prior, why would they think that, like, let's assume that even if this was not advertised, not advertised, right? Let's assume that we know that this other person is going to play not advertise, right? This would be the ideal outcome. Is one person is going to play advertise, the other person is going to play not advertise. But if we know that that person is going to play not advertise in that last round, then I'm just going to try to get it around early. And the same person is going to think the exact same thing, and this is going to stem all the way back. And so we were going to be at AA from the get-go. And so the number of rounds also heavily influences the different patterns that we could have here, right? So when we're thinking about this repeated game and this sequential game, right? Um, oh, this is just, that was the same thing. Another way that we could think about this is in a sequential, no, because we're not moving at the same, I mean, we're moving at the same time. So we're just going to skip this one. I mean, this here in order to make everything complete. Again, I made these slides before the weekend, and now it is the weekend. So we're here. A sequential game then means that a leader and one or many followers happens. So a leader is going to make the first move. The Stackelberg leadership model is a strategic game where players compete on quantity. So the first stage, the leader is going to decide on quantity produced, and the second stage, the follower is going to decide on the quantity. This is very similar to our game up here, right? So we'll just move this down, and we'll kind of talk through this example here. So again, a leader. So let's assume that LG is our leader. They're going to move first. We're going to make our first move. And then, so the first stage, the leader decides on the quantity produced or whether or not to enter. And then the second stage, our follower is going to decide whether or not how much they should produce, depending on what the producer does. And so that will end up from some following conclusions. We're going to decide on quantity produced. And so this will lead us to solving the sequential game. We talked about this a little bit at the top, but solving a sequential game is really easy. So to predict the outcome of the Stackelberg game, we're going to use a strong version of the Nash equilibrium. And so these set of strategies are going to form what we call a sub-game perfect Nash equilibrium. And so this is going to be if the player strategies are in Nash equilibrium in every subgame, it is going to be a subgame perfect Nash equilibrium. And so we can solve for the subgame perfect Nash equilibrium using a backward induction, where we first determine the best response for the last player to move. So remember in here, we chose these two options first, right? So essentially, we're choosing the best response for the follower, depending on what the leader is going to do. And then we're going to move up to the next layer, to the next layer, to the next layer, and we're going to find the best response for each player's from the next to last move, and then repeat that process until we reach the top for the first mover. And so now let's look at this, right? Let's look at a different example. We're going to go back to the American and the United example, right? So if American was our leader and United was our follower, what would we do? Well, let's first look at the payoffs for United first, right? So suppose that American is going to perform at 48, right? Then United is going to pick 5.1. Suppose that American is going to pick 64, then United is going to pick 4.1. Suppose that American is going to pick 96. Well, then that means that United is going to pick 2.3. And so now we can ignore this outcome, this outcome, this outcome, this outcome, this outcome, and this outcome, because we know what United is going to do regardless, right? So now American just has to choose between 3.8, 4.1, and 4.6. And obviously, they're going to choose 4.6 because it's the best option. And so that leads us to this pathway being the dominant strategy. So let's play a game. Oh, we already did this one, I think. Ford and GM. I mean, we can do it again. It's the LG Panasonic game. Um, would GM have an advantage if they were the first mover? So, in a static game, right? If Ford decides to enter, GM should not enter. If Ford decides to not enter, GM should enter. If GM decides to enter, Ford should decide to enter as well. If GM decides to not enter, Ford should decide to enter. So let's think about this. If we wanted GM to go first, they have a decision to enter or not enter. And Ford has a decision to enter or not enter as well. If GM enters and Ford enters, so again, we're going to go GM Ford in our payoffs, it is going to be minus 150, 50. If Ford decides to not enter, but GM decides to enter, Ford is going to get paid 0, and GM is going to get paid 875. If both of them don't enter, it's going to be 0, 0. If GM decides not to enter, but Ford enters, it's going to be 1500 to 0. So to look at this, let's go backwards. Assuming GM is going to enter, so assuming that we are on this side of the tree, Ford's best response is to enter, right? Because 50 is bigger than 0. Similarly, on this side, if GM doesn't enter, oh wait, shoot, sorry. I think I wrote these backwards. I'm gonna lose my mind. I'm gonna lose my mind. I'm gonna lose my mind. Yeah, Ford's payoff should be written here. Oh wait, no, 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 no. Ford's payoff was right. That one was correct. Um, this one is incorrect. Yes. Okay. So if GM decides not to enter, Ford should still decide to enter. And so now GM is choosing, do we want to go this pathway or do we want to go this pathway? Well, choosing between those two, they should choose not to enter. So we should be here. And so, no, GM does not have a first mover advantage because Ford is always going to enter. So another example here, this is what we call an ultimatum, I mean a dictator game. The dictator's decision is to offer a deal, and the second player gets to choose to accept or reject it. If they reject the game, I mean the offer, then there is going to be no decision. The deal will fall through, right? So everybody is like, oh, I'm just going to not accept any offer that isn't fair as the second player, right? But looking, if we reject or if we accept, it would be better for us to accept, even if we were offered only a cent. Similarly here, it would be better for us to accept $25 than nothing. And so this other player, player one, is obviously going to choose to keep 4.99 compared to $25. And so although you would think that the 25-25 was the best outcome for everybody because it's the most equitable, the 49.99 0.01 is the one that wins out because of backwards induction. And that's game theory. So it seemed kind of complicated at the first, but if you just draw your game trees correct and you draw your game boxes correct, it's pretty simple to solve just about anything. And so we talked a lot about repeated games and sequential games and static games and everything. And so hopefully you guys will be good enough at this stuff. You guys will be pros to ace this on the final. I think game theory is really, really cool. If you want to come talk about this, because we'll be closer to the semester, hopefully by the time that you guys get this. Um, Let's come chat. I love talking game theory. So thanks everybody for watching. And the last chapter should be posted here soon. Thanks.